Good afternoon, I'm Mr. Ish. Thank you for joining me. If you think about the video that was presented prior to this one where we addressed the concept of radius of convergence and interval of convergence, I can understand several students thinking of that video and coming out slightly confused and some not being confused. In this video we lay all of that to rest. It's always a delicate balance between idealism and realism when you're basically instructing a student on a difficult concept. How practical do you want to make it, or how realistic do you want to do it, versus the idealism behind it or the theory behind it. I'm pretty confident that most of the students watching these videos are primarily interested in passing their calculus classes, getting their A or their B, and then perhaps never looking back to calculus again. A small percentage of those students will go on to go into higher level math and or PhD. For those students, then there's the ideality or the idealism which is involved, but the primary viewers of these videos are the ones who practically want to learn calculus, and you have to be realistic with how you do it. In this video I'm going to be quite realistic and practical with this. We have already talked about the radius of convergence and the interval of convergence. Here we find it and we hone in on that in terms of the practical items you want to know. The series converges for power series, generally and particularly for power series. We have convergence by three cases, and you know I've talked about this in the previous video. Here I make it more clear. You can have a case where x is equal to only a specific value where it will be convergent. In all other instances it will always be divergent. Here you have a radius of convergence which is just basically 0. I'll talk about the radius and interval in a very practical manner very soon. You would have an interval comprised of only a single item. Case number 2, all values of x. X is an element of all real numbers. All those values of x placed in your power series will give you your convergence. There is little to no manner by which you will get divergence. Here your radius of convergence is infinity. Your interval of convergence minus infinity to infinity. All these values create convergence. Case number 3, you have a combination of x values which will create convergence and a combination which will give divergence. The previous video I showed you two questions which are basically on case 3. Here in this video I'll show you one of this, but I'll show you and clarify with regards to these two over here. A single example focusing on this, but I will also talk about this. The radius of convergence is to be determined, the interval is to be determined. I want you to think about the radius of convergence as this, your spread. If you have a given x value which can or cannot create convergence, how much do you spread on each side in terms of the possible x values that will create you convergence? You can have little to no spread, or you can have an enormous amount of spread. When only a single value can create you that convergence, you have little spread, hence your radius of convergence is 0. When all the values can create that convergence, you have an enormous spread. All the values, you have a spread equivalent to infinity because your interval is that large. When your spread is somewhere in between, you have a combination developing out, then you know what your spread is. It's a minuscule spread, but it's not negligible, but it's not infinity as in this case. I want you to think about your interval of convergence only as a notation which clearly notates your spread. That's all what it is. Think about in these practical terms, and I guarantee you the concept of radius of convergence and interval of convergence will not be as hard as you would imagine it to be. Now let's focus in on our two questions, but before those two questions I'm going to digress only a little bit, but for your benefit on this 1 and 2, because that's something which requires a little bit of attention. I will give you still a complete example regarding case 2 and a complete example regarding case 3. I'm just doing this minor digression in regards to 1 and 2. Consider a specific series which looks like n equals 0 or 1 up to infinity. You have a specific rule over here. At the end of this rule, using a ratio test, you've arrived at something which looks like this. Absolute value of x, limit as n approaches infinity, you have something like this. It's just a normal general thing. You could have had anything in here, but so long as it was something like this, such that when you would do this limit evaluation, you'd always get infinity. All of this would boil down to absolute value of x and infinity. This is what you're getting out of that ratio test for a specific series you have. When you're looking at this, what case do you think you fall into? Is it either 1 or 2? If you're thinking 1 over here, you're right. Why are you right? Because in all instances you're approaching towards a series divergence. The only way you can stop that or prevent that from happening is if in that series rule you were to plug in a value of 0, and now your entire series will tend towards 0, and then you would see convergence. And that would be the only case. Here x is equal to a specific item, only a single item. Here x would equal to 0. Your notation would be just this. Your radius of convergence, that is the spread of possible values, is 0 because you have little to no spread. It's only a single value and there's no spread around that value. A single value can only be deemed to create convergence, whereas everything else creates you divergence. That's case A, case 1 I mean, and you can see it's not that hard mentally to grasp. Now let's look at a case 2 scenario. How would everything change with regards to what I'm showing you over here? It will, and I'll show you how. You're looking at a series by means of the ratio test. You arrive at something which looks like 1 over, let's just say, n plus 2 to the power of n, hypothetically. Now when you put limit as n approaches infinity, you're always gonna, in this part, arrive at 0. What does that tell you? It means outside of your x component of your power series, remember power series has your variable and your coefficient component, outside of the x component you're already, in terms of your n values, already looking at convergence. You're looking here now at case 2, because now any value you put, irregardless of what this is, any value you put, you'll always have convergence. Therefore, not only do you have a single value which will give you convergence, but you have a huge spread on either side, minus infinity to infinity. You have a radius of convergence here equal to infinity. This here would have been your x value based on what you're coming out from here, which would really be 0. 0 times x is 0. You have a huge spread over here. What would your interval of convergence be? It would be exactly what I was telling you. Practically, you think about a notation in which you formalize your radius of convergence. It would be minus infinity to infinity. Why? Because when you're already zeroing out your entire series in terms of convergence with the n components, the x components can adopt any value regardless of what that x might be, any value, and you'll always see convergence. Hence, x can adopt any value from minus infinity to infinity. Your radius of convergence is that broad, it's infinity. Keep that in mind. That little practical advice or suggestion I'm giving you with regards to 1 and 2, keep that in mind. Always keep that in mind. Now let's look at our 2 questions for this particular video. Our first question is this. We have from n equals 0, infinity, x to the power of n divided by 2n factorial. If you put 0 here in place of factorial, 0 factorial is not a 0, it's always equal to 1. You cannot zero out your denominator. When you're seeing this, you should always be thinking about what I told you. N plus 1 factorial is always equal to n plus 1 times n factorial, a useful shortcut to remember because it comes into play. Everything always by ratio test. an plus 1 and an. What are these terms? Well, an plus 1 will be x to the power of n plus 1 divided by 2n plus 1 factorial. You see how it's coming into play? You have to know that. Nth term is exactly what you're looking at, x to the power of n divided by 2n factorial. You're doing the ratio of these two always in terms of absolute value. When your ratio will be what? It will be limit as n approaches infinity. You're seeing x to the power of n plus 1 divided by 2n plus 1 factorial all over x to the power of n divided by 2n factorial. Open this up. You have x to the n, x to the 1 divided by 2n plus 1 factorial. Multiplied by, separate this out, you have 2n factorial divided by x to the power of n. Now think about our shortcut. Our shortcut is right over here. Bring it into play right over here. Why don't I bring it into play? I can. N plus 1 factorial, you'll always have, remember the 2 is coming out from right here. There's a 2 in the function. It'll be n plus 1 times n factorial. Cancel out your like terms. 2 cancels out. N factorial cancels out. X to the n cancels out. What remains? You have on the top x. You have on the bottom n plus 1. That right there is representing what remains from your ratio test with regards to limit. You've seen all of this come into play. Allow me to erase it, now evaluate that. What I have is x absolute value divided by n plus 1. I can bring the absolute value x over here, and I'm looking at 1 over n plus 1, which I can bring in an absolute value. Look at this, limit as n approaches infinity. What will happen over here? All of this will zero out. You're looking at 0 absolute value x, you're looking here at 0. This goes right back to exactly what I was showing you with regards to case 1 and case 2. There is no value of x for which you can generate that you will see divergence, because every value will generate convergence, because your n components here will always give you convergence. What are you seeing here with regards to your radius of convergence? It's going to be infinity, because you can put any value here in x. It'll always get zeroed out by means of the limit. You'll always tend towards 0. Your entire series will tend towards convergence. Your radius of convergence is infinity. Your interval of convergence is minus infinity to infinity. rewind back to the beginning of this video, case 1, case 2, case 3, this right here falls into case 2, and it's easy. You can see it's not hard. That little practical suggestion or advice I gave you when I broke down 1 and 2 by means of an example, this falls into that number 2 case in that example. You see 1 over n plus 1, this zeroes out, it zeroes that out. Every value here of x can give you convergence because your main n component here will give you convergence anyways. This here is your final answer, so this question has been done. In terms of our second question, a good question, let's focus on this. N equals 0 up to infinity. We have n times x plus 1 to the power of n divided by 2 to the power of n plus 1. Again, employ the ratio test and see what happens. When you apply the ratio test, we're going to do that. You're going to look at your an plus 1 term, and then you look at your an term, always an absolute value. When you're looking at this, you know what you're going to have. You're going to have n plus 1 times x plus 1 to the power of n plus 1 over 2 to the n plus 1, which is n plus 2. When you're looking at your an's term, that right there is your an term. You have exactly that, which you can copy down. When you're looking at this ratio test, you're doing the ratio of these two. You can open up everything here with regards to your laws of exponents. You'll have this, you know the drill now, divided by 2 to the n, 2 to the 2. Multiply this in terms of its reciprocal, because it was in the denominator, it flips around. You have 2 to the n, 2 to the 1, divided by n, x plus 1 to the power of n. Now determine all the items which cancel out. This cancels out with that. This cancels out with that. This 2 to the 1 cancels out with this. 2 square, but only with the square component. What remains? This, that, and that. You'll have limit as n approaches infinity. You're having n plus 1 divided by n. That's this part. Then from here, the non-n components, I have absolute value x plus 1 divided by 2. It's not hard to evaluate this. This will always equal to 1. You know this by now. This 1 will multiply with this part right here. You'll always have x plus 1 absolute value divided by 2. That's exactly what you generate. A very interesting thing, in terms of the ratio test, this is less than 1. Based on the ratio test, you have convergence less than 1. You take this on the other side, you have absolute value of x plus 1 is less than 2. Here is where you have determined your radius of convergence to be 2. Your radius of convergence is equal to 2. We have a little sunlight falling on the board. It shouldn't be a problem though. You can do the absolute value algebra here to determine your intervals. X plus 1 is less than 2. You'll have x plus 1 is greater than minus 2. X is less than 1. X is greater than minus 3. I'm seeing an interval such that it's this. But I need to fine tune this interval and see if there's any change in those inequalities with regards to these endpoints. Are these endpoints included or are they excluded from the convergence aspect? We have to find that out. It's not hard. You can utilize basically a good specific test, a test for divergence. We've never really talked about it, but it's intuitive. And let me talk about it with regards to this. You would bring everything here with regards to the minus 3 value and the 1 value into place of x. Your everything here will become this. You'll have n. When you put minus 3 in place of x, you'll have a minus 2 to the power of n divided by 2 to the n plus 1. When you put 1 in place of that, you can also do the integral test if you want. Sometimes the integral test is easy, sometimes it's hard, as you know. You bring in the x value of 1, you'll have n, 2 to the power of n divided by 2 to the n plus 1. You can do a little bit of fancy algebra here and clean things up. You'll have n, you'll have minus 1 times 2 to the power of n divided by 2 to the n times 2 to the 1. You see I'm splitting things up. Here I'll have n, 2 to the power of n divided by 2 to the n, 2 to the 1. You can cancel things out. When I'm looking at this cancels out. This right here boils down to n over 2 from infinity to 0. You know, if you were to do the integral test over here, this would actually be a divergence, a clear case of divergence. And yeah, when you do this, you can separate this out. You have n times minus 1 to the power of n, 2 to the power of n divided by 2 to the n, 2 to the 1. This cancels out. Everything remains as n over 2 times minus 1 to the power of n. All of this boils down to that, all of that boils down to that. You can do the integral test here and get divergence. You'd have to do something other than an integral test here, because this right here might be a difficult integral to do. Unless you can do it, you can do it. In both cases, you'll have divergence over here, and we will talk about that. But in both cases, this right here is good. These endpoints are not involved. Your interval of convergence is really this. You'll have minus 3 up to 1. Neither value is included, but any value in between is convergent. Any value outside is divergent, including 1 and minus 3, because you don't have equal signs over here. Let's talk about that divergent test. If you were to look at this in terms of a limit as n approaches infinity, you really have 1 over 2n. When you do this, 1 over 2 limit n, it does not equal to 0. Based on the test for divergence, if it does not equal to 0, it's divergent. So obviously this here is divergent. When you look at this, I'll do it right over here. The test for divergent is not a very difficult test to understand. If the limit n approaching infinity does not zero out that function you're working with, you don't have convergence, you have divergence. If it zeroes it out, you have convergence. But the test for divergence, if you don't get that zero in terms of the limit, you have divergence. Let's look at this. You're looking here at you have n over 2 times minus 1 to the power of n. You can bring out the 1 over 2. You're looking here at limit as n approaches infinity. You really have minus 1 to the power of n. Then let's not forget the n which sits right out here. When you have this evaluating in terms of infinity, you're really looking at 1 over 2 times infinity times minus 1 to the power of infinity. This obviously is not going to zero out. Based on the test for divergence, this will be divergent. Based on the test for divergence and integral test, this will be divergent. Because you can do integral of n over 2, it's very easy, it's a polynomial. You'll get an n squared over 4, you put infinity and 0, you'll have divergence. Test for divergence shows this to be divergent, test for divergence shows this to be divergent. Just look in your book and look at the section on the test for divergence. I have not talked about it because it's intuitive and it's easy. Limit for that function, if you're looking at, if it does not zero it out, that function is divergent. If it gets zeroed out, it's convergent. But in all instances, placement of these endpoint values leads you to divergent outcomes. Those divergent outcomes seal you in terms of the notation to be this. You have no equality here with regards to equal sign. Everything is not including the endpoints. The radius of convergence 2, the interval of convergence minus 3 and 1, not including those. And that brings us to the end of this video. Thank you for watching. Have a good day.